And this will finish off our chapter 4. So a relation here is a pairing of numbers with a domain and a range. So kind of like on your skill test, you have a pairing of numbers. You had a domain that you had to come up with, and then a specific range that went with it. So a pairing of numbers with domain and a range. Relation is it's really just a set of coordinates. That's all it is. Okay, a set of coordinates. Dots on a graph. That's what a relation is. And sometimes we connect the dots, sometimes we don't. When we connect them, it's called a continuous relation or function. And when we don't, it's called discrete. The domain is the set of independent variable values. And for our purposes, we've been calling X the domain. We've been primarily using X as the domain, but you don't have to. But it's the input numbers. The domains are the inputs. So you might want to even put that on there. It's the inputs. It's the values that you're putting into the function that I've been having you choose, like -1, 0, 1, 2. And the range is the set of dependent variable values, or the outputs. So you might want to write on there inputs and outputs. So the domain is inputs, range is outputs. In your classwork today and homework, you'll be asked to find the range. It just means find the outputs. What do you get when you plug the domain or the inputs into the function? So while a relation is just a pairing of numbers with a domain and a range, there is a special kind of relation called a function. We've studied the linear function. We've studied a little bit of x squared functions and x cubed functions, and 2 to the x function and the 3 to the x function. So we've studied some other types of functions a little bit, but primarily we've studied the linear function. There's a test that you can use to decide if a relation is actually a function. It's called the vertical line test. And the vertical line test says if any vertical line passes through a graph more than once, then it is not a function. So it's a test to see if it is a function or not. And I'll show you an example of that test on a set of points or a relation later. So what you'll do with the vertical line test is you'll be given the graph of a relation, just a set of points. They may or may not be connected on a graph. And you're asked to see, is there a vertical line that passes through more than one point of the graph of that relation? And if there is, then it's not a function. If you cannot find a vertical line that passes through more than one point, then it is a function. The way I think about it is if there are any 2 points stacked directly one on top of the other, it's not a function. Okay? You ever have 2 points stacked exactly one on top of another like this? It does not pass the vertical line test. So there's a point there. There's a point there. There's my vertical line, just to review what a vertical line is. If there are any 2 points stacked one above the other, it's not a function. And as you move on into math, you'll find that we have function graphing calculators. If you want to graph something that's not a function, like a circle, or something we call an ellipse, which is kind of an oval, you have to do it in 2 stages. You have to do the top half and the bottom half separately, because it's a function graphing calculator. It will only graph functions. It will not graph relations. Of course, there's software that will do that for us. There's computer software that will graph relations just fine. But our graphing calculators handheld won't do that. Function notation. F of x reads as, quote, f of x, and replaces y. And we use function notation when we have a function and the x serves as what we want to plug into the function. All right, here's an example of a function, y equals 3x plus 1. There it is in function notation. We'd say f of x equals 3x plus 1, or g of x equals 3x plus 1. As you move into higher level math, we might use a letter that represents something like s of t would represent position. You might guess speed, but it's actually position. V of t would represent velocity. And a of t would represent acceleration. Things in physics, we use function notation all the time. Letters that represent specific physical, real-life things. So y equals 3x plus 1, that's a linear function. And f of x equals 3x plus 1, that's function notation for that line. Right, so things we'll be asked to do is identify the domain and range of each relation. So you'll be given a list of coordinates. These are just x, y coordinates. Remember, the first one is x, the second one is y. And we're just going to list for the domain. I just do a D for domain, so do that. Write a capital D for domain. Fancy brackets, like this. That's set notation. And what I'm going to do is look through all of my x coordinates here, 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 and here. And I'm going to put them in order. So I'm going to place them in order with no repeats. Now, fortunately, for this list, it's already in order, it looks like. So in order, no repeats. And I don't see any repeats either. So I have -2, 0, 4, and 5. That's my domain. Okay, we call that the domain. Just listed in order, no repeats. And then the range, I'm going to look at just the y values here. I have 0.5, 2.5, 6.5. You see how this one and this one is repeated? So I'm not going to write it twice. I'm only going to write it once in my list. So draw a capital R for range. Do fancy brackets for the set. And we're going to start with the smallest number in the list of all the red circles I have here. These are all the y values or dependent variables. I have 0.5, 2.5. I'm only going to list it once. And then 6.5. And that's my range. And then we're going to be asked to do something else here. It says represent the relation with a mapping diagram. So we're going to do that next. So a mapping diagram looks like this. We have two little ovals, one here. We're going to label this the domain oval. And then we have another one. We're going to list that as the range oval. Domain and the range. And the domain has the following values. -2, 0, 4, and 5. And the range has the following values: 0.5, 2.5, and 6.5. And then what we're going to do is go back to the original up here. Back up to the original. And draw little, I guess, lines to connect them. It's kind of like a matching. So -2 goes with 0.5. And 0 goes with 2.5. And 4 goes with 6.5. And 5 goes with 2.5. So that's the mapping diagram. This is the mapping diagram. And then the final thing that we're going to do with these is answer the question, is the relation a function? And to answer that, here's what we're looking for. Remember what I said, you can't have 2 points stacked one above another if it's going to be a function? You can tell very easily in the mapping diagram if you have 2 points stacked, one above the other, if there are 2 lines coming from one value of the domain, it's not a function. So we're going to look for 2 lines. So maybe write this down. If 2 lines come out from one D value, it's not a function. So that's what we're looking for. 2 lines. That's not cooperating. 2 lines come out from one D value, it's not a function. So on this one, if I were to graph this, like -2, 0.5, 0, 2.5, 4, 6.5, and then 5, 2.5, as you look through here, do you see 2 lines coming from the same D value or same X value in many cases? No. There are, there are 2 lines going to this 2.5 over here, but that doesn't matter. So this is what we call a function. So you can write underneath it, this is a function, or to the side of it, this is a function. So it is a function. I'm going to give you an example of one that's not a function next. So that one is a function. And then I'll show you graphically what it would look like. So domain, what's the domain here? Can you list them in order? They're all jumbled up here. What's the smallest of all the first coordinates? 4 is. So you scan it, you find the 4, put it in the list. And the next one is 5 and then 6. And you only list the 6 once. And then the range. What do we got here? Scan it. What's the smallest of the range? 3. So you put the 3 in, and then the next is 4, and then 5, and then 8. So list them in order. And you draw your 2 little ovals here. You got a D oval and an R oval. And we list our 4, 5, and 6 in the D oval. And we list our 3, 4, 5, and 8 in the R oval. And then we start connecting them up, going back to the original. 6 goes with 5. 6 goes with 5. 4 goes with 3. 6 also goes with 4. And 5 goes with 8. Here's what I mean by 2 lines coming out from one D. Do you see that? So that if I were to graph this, here's what this would look like if I graphed it. I would have a point at 6, 4 up here, and also at 6, 5 is the other one. So I would have 2 points, one stacked above the other, so that if I were to draw a vertical line through those 2 points, you'd see that it goes through both of them, right? But there's 1 point stacked above the other. That's what we're seeing right here from the 6. So this is not a function. So if you were to try to graph this on your graphing calculator, or graph an equation to go with it, it won't work. It's black. This is a relation or collection of points that is not a function. Why don't you go ahead and see if you try this for the next 2. See if you can find, you're going to find one of each in the next 2. See if you can list the domain, the range, to the mapping diagram, and then decide if the relation is a function. I'll give you just a minute or 2 to do that. All right, so on this first one, you can see we have, you can see it in the original coordinates, but because we have 2 4.2s, both going to different numbers, that's going to stack one a point above the other. So this one right here, because of what's happening in our mapping diagram here, we have 2 lines coming from one of the domain values, the 4.2. This is not a function. And this one over here, you'll see there's only one value coming from each one. You can look in the list up here, see -1, -2, 4, and 7. They're all different, 4 different x values, 4 different domain values. So this one is a function. So it's kind of a combination of looking at it, checking to see if there are any points one stacked above the other. You can see it visually in the mapping diagram here. See the domain and range. And then we're going to show you how to see it geometrically as well on the graph. All right, so geometrically, here's how we check to see if a relation is a function. You'll see a collection of points here. Do you see this collection of points? Looking at your paper, is there any vertical line you could draw that would hit both of those? Do you see the vertical line that you could draw? So, like, I could draw a vertical line through here and here and here, and then, wait a minute. When I draw a vertical line through there, okay, I'm drawing vertical lines everywhere where I see a point. Okay, and if at any point I draw a vertical line that goes through 2 points, it's not a function. So that's what you're looking for. For example, this one right here, I could draw a vertical line anywhere on here. Anywhere I draw a vertical line, it's only going to touch at 1 point. Okay, this is an upside down parabola. A parabola that's facing upward or downward is a function. So you just write function. That's the vertical line test. Pretty easy to do. See if you can find any vertical lines to go through the more than 1 point down here. You're looking at it, it looks like, well, maybe I could, but start drawing them here, see what's happening. I don't think I can. I can't find one that goes through more than 1 point. So this one is a function. And then this one we've got to do some plotting of points before we can tell. But 0, 4 would be up here. -2, 2 is right here. 0, -3 is here. 1, 5 is here. I could have stopped with the 1, 5 is up here. 4, 2 is right here. But right here, here and here, I have 2 points that both have the same x-coordinate of 0. So for that reason, this is not a function. So the vertical line test is a real visual way to be able to see if a relation is a function or not. It's really easy to check. And visually, you should be able to just look at it and see, are there 2 points, one stacked above the other, anywhere on that graph, and then you can say it's not a function. The function w of x equals 250x represents the number of words you can read in x minutes. How many words can you read in 8 minutes? So just a little bit of function notation. W stands for words. X is what you're plugging in. So W of 8 means this. You're going to take 8 and plug it in for x in that equation. It's a linear equation, a linear function. 250 times 8. And so what we're saying is W of 8. So in words, this is W of 8, or words read in 8 minutes, and we get 1,600, 2,000 it looks like. So 2,000 words. What would the notation, how would the notation change if you were to find how many words you read in 6 minutes? We would be looking at W of what? 6, yes. W of 6. And W of 6 is 250 times 6, which equals 1,500 words. And how would it change if you were finding an hour? How many words you can read in an hour? This would be W of 60. So it would be 250 times 60, which is going to add another 0 to my 1,500. So I'll be up to 15,000 words. But that's what we mean by f of x, or function notation. So when I'm asking you to plug in -1, 0, 1, and 2 for x, I'm just asking you to find f of -1, f of 0, f of 1, f of 2. So that's what we're going to do next here. They're going to ask you to find the range of a function here. It says the domain of f of x equals -1.5x plus 4 is 1, 2, 3, 4. What is the range? So we're going to find the range by plugging in all values of domain. And then we're going to list the range in the end. So we're going to use our f of x notation. So f of, first one is 1. F of 1 is -1.5 times 1 plus 4. -1.5 times 1 is -1.5. Add 4 to it, and we get 2.5. So that's the first number of the range. So if I were listing the range out down here at the bottom, I have my first number would be 2.5. I might wait to list it out because I want to list it in order from smallest to biggest. But I would put a 2.5 somewhere in this list. F of 2 is equal to -1.5 times 2 plus 4. So that's -3 plus 4 is 1. And then f of 3, I'm doing the third one right here, is equal to -1.5 times 3 plus 4. It's -4.5 plus 4 is -0.5. And then f of 4 is equal to -1.5 times 4. And we've got plus 4. So -4, -6 plus 4 is -2. So now I'm prepared to list the range in order from smallest to biggest. So I put my big capital R for range, my fancy bracket for set notation, and list them: -2, -0.5, 1, and 2.5, and that's my range. So you could, I'm showing the work here. You know, on a linear function, you could probably plug these in your head and list the range. It's good to show your work, though. So if I'm, checking your work and can give you partial credit, I give you partial credit even if you mess up on a sign error or something like that. So it doesn't hurt to share work, but you could do this in your head, especially with a linear function, right? It's not hard to do. I don't know. For example, could you tell me the range on this one? You could do it in your head. I don't know if we can do it in order in our head. Think about which number in this domain will give you the biggest number and which will give you the smallest. This one detail. So we plug 1 in, right? If I plug 1 in here, what do I get? -8, right? So -8 first. If I plug 3 in, I get 4 times 3 is 12, minus 12 is 0. So I have -8, 0, and then plug in 5. 4 times 5 is 20. 20 minus 12 is 8, and then plug in 7. 4 times 7 is 28. Minus 12 is 16. So, I mean, that's all that I need. I'm just asking, what is the range? What do you get when you plug in those 4 numbers of the domain? Okay, so we're just plugging them in. And of course, this up here would be the work, if you're going to show what you're doing. All right. Now, when it comes to real-life problems, there's definitely a reasonable domain and range. For example, you have 3 quarts of paint to paint the trim of your house. A quart of paint covers 100 square feet. The function a of q, you put in the quarts of paint, kicks out the area that you could cover with that many quarts of paint. So a of q equals 100 q represents the area in square feet that q quarts of paint cover. What domain and range are reasonable for the function? What is the graph? Now in this case, we're going to write our domain not as a list of numbers, but as a compound inequality. So I'd like you to write D, capital D, and then this time we're going to write it like this. Put the x over here in the middle with little less than or equal to symbols on each side of the x. Well, from x's perspective, this is saying it's greater than or equal to a certain value. and also less than or equal to a certain value. Now, if you have 3 quarts of paint at your disposal, you could use 0 paint. Maybe you decide to watch TV all day instead of paint, right? So you don't paint at all, so use 0. You're not going to cover any square footage, so you could have a 0 over here, right? You could use 0 quarts of paint. You could decide not to do anything in terms of painting. Or you could use up to and including 3 quarts of paint. So that's your reasonable domain for this real life problem. Because you can't use negative quarts of paint, right? 0 is the smallest you can use. You can't use more than what you have unless you go buy more. Okay, so 0 to 3. What about the range? Now here's what I want you to do. Write a big capital R. And instead of putting, oops, I shouldn't have put X, I'm sorry. It really should be Q. If you want to leave it X, that's fine. But if you're going to leave it X, then in the middle here you need to put A of X and not A of Q. Sorry about that. Forgot we were using Q instead of X. If you can change that, change it. If not, just write A of X here. That's fine. And we'll use X for quarts of paint. So if I plug in 0 to this equation, A of 0 would equal 100 times 0, or 0. So if I put in A of 0, I get 0. That makes sense. If I don't use any paint, I can't cover any square footage, right? If I plug in 3, A of 3 is equal to 100 times 3. So the biggest amount of area that I could cover would be 300. And so by plugging in the endpoints of the domain, we get the endpoints of the range. So this is a continuous function. You could use anywhere from 0 to 3 quarts of paint. So go ahead and label that. They call it the x-axis. It's actually the q-axis. 1, 2, or 3. And then in terms of square footage, it could probably go by hundreds here. 100, 200, 300. And we could graph it. We could start at 0, 0 if you want. If I plug in 1, I'll have 100 square feet. If I plug in 2, it would be 200. If I plug in 3, it would be 300. And I could connect the dots because it could be anything in between. I might only use 1.5 quarts of paint, which would give me 150 square feet of coverage. Okay, but anything in there is what I might use. I might decide to wrap the paintbrush up and saran wrap, put it in the refrigerator, and come back to it later. Yeah, wrap it in saran wrap, put it in the refrigerator, come back to it later. If you have 7 quarts of paint, what would the domain and range be here? What would change for my domain if I have 7 quarts of paint?
7.
We'd have Q in the middle, and it would go from 0 to 7 for the domain. And what about the range? What would the range A of Q be? If I plug in 0, I get 0 square feet of coverage. If I plug in 7, it would be 700. And so that's the only thing that would change in that problem. Okay. So is f of x notation new for you? Have you seen that before? Have you heard of domain and range? Have you guys heard of domain and range?
Yeah.
Have you heard of the vertical line test? Deciding its function thing. Probably haven't used function notation a lot. Probably not at this point. When you start combining science with math, when you start doing physics, you will use function notation. You'll use it a lot in Algebra 2. You won't see it much next year in geometry. Go ahead and write your summary up. You might want to write something along the lines of the domain. What is the domain? What is the range? Maybe you learn function notation for the first time. Maybe something about if 2 points, 1 point stacked above the other anywhere on your graphing grid, it's not a function. Maybe write that out. Maybe that's something new for you.